All right, we're talking about series. What's the difference between a series and a sequence?
Series is addition.
Addition. Series. Yeah, series is a sum of the terms of the sequence. Sequence is a list of terms. Series is the sum of the terms. And we talked about what constitutes a sequence converging or diverging. But the more interesting and also more challenging question is, does the series converge or diverge? If we started adding up all the terms, does that sum converge or diverge? And one of the ways to determine if it converges or diverges is by looking at the sequence of the partial sums. So we started this one yesterday. We want to know if the sum from 1 to infinity, the infinite sum of the terms generated by 1 over n, if that sum grew infinitely large or it converged to a finite number. So we looked at the sequence of the partial sum. So we got the first term was 1, the sum of the first two terms was 3 halves, and we got all the way to 2.45, which was the sum of the first 6 terms. And because we were running out of time, we said that must diverge to infinity. But since we have more time and I have my calculator here, I want to add a few more terms. The next term would be the 7th term, which is plus 1 over 7. And I'm not going to write these down, but there would be the next term, 2.59, and then plus the next term, that would be 2.717, plus the next term would be 1 over 9, it's 2.8, so on and so forth, plus 1 over 10. And you go out far enough until you're convinced that either it will converge to a finite number or it will not. Now, we've gone out 11 terms, and already you can see that each time it is increasing as we expected, but it doesn't appear to be like just increasing further down the decimal line. We're still increasing in the tenths, which is making the unit now jump up to the whole next integer level of 3. So this one is still not 100% conclusive, but the evidence points to the fact that over time this one will grow infinitely large. And it does, okay? So now we're back to this one here. The first term is 1, so you would write that down. I'll go ahead and write it down. 1. And then you add the next term, which is 1 over n squared. So when n is 2, you get 1/4. So here would be the second partial sum, 1.25, plus the next term would be 1 over what? 9. That's 1.361, plus now we're on the fourth term, so that's going to be plus 1 divided by 16. That's 1.423. I'm going to quit writing them down now. The next term would be plus 1 over 25. And then plus 1 over 36. And then plus 1 over 49. Plus 1 over, what would be next? 81? No, 64, sorry. Plus 1 over, that's 81. And then finally plus 1 over 100. Let's do one more. Plus 1 divided by 11 squared, which is 121. All right, so at least we've done the same number of terms for both. Now, if you look at the numbers here, the data, it's kind of the limit idea, right? They do appear to be increasing, but now already, as they increase, they're increasing a lot more slowly. And looks like we're kind of leveling out around 1.5 something. What do you think this one does? Converges or diverges, based upon the sequence of the partial sums? Converges, okay? And that would be the correct answer. This one actually converges. Now, to what? I don't know. We could maybe go out many, many, many terms to see, and that could be helpful. Is there a way to do that on the calculator? Yes. Let me show you. If you hit alpha window, you get a shortcut to a lot of nice commands. Look what number 2 is, summation. And this is kind of a new one that they've added to the calculator. This used to not be on the calculator. You used to have to do a sum of a sequence. But now they have the sigma on there. So let's go from x. We'll define it from x equals, where do we start? 1. and let's go out to 11. That's what we just did. And we'll type it in as 1 divided by x squared. So when you type it in like this, your calculator knows that x is a positive integer. It knows to count by ones. So this should give us the same answer we have above of 1.558. See that? It just does it on its own. So with that in mind, and this is kind of a nice thing, you don't have to actually look at the actual sequence of partial sums. We can get straight to business, can't we? Instead of listing the first 11, we can just go way out to what? 1,000? Yeah, that might be, I don't know. I don't know if that'll break the calculator. I'm going to try 100. 1.63. Now, we do want to compare that to, we do want to compare that to what? You want to compare that to another number. You don't want to just do 1. Let's compare it to another number like, I don't know, let's try 1,000. You said 1,000? Maybe it'll take it. Oh, a little longer. What's up, calculator? Come on. And now when you compare these two numbers, one that's way down the line and one that's way, way down the line, you compare them. Now there should be definitive mathematical proof that this series does, in fact, what? Converge. And it converges to somewhere around 1.64-ish, right? Maybe 6.5-ish. But it's probably going to be 1.6-ish. Okay? Let's go ahead and do the same thing for 1 over n, because we only listed out the first 11 terms. So let's delete that. And that was the first one. So the first 1,000 terms, seven, and then let's go crazy past 1,000, like 10,000. I wonder if that's going to break the calculator. Yes?
When I did that one to 1,000,000, it waited a while, like 5 minutes, and said error break.
You broke the calculator officially. It said error break. It took 5 minutes, but you broke the calculator. Yeah, so mine is still working. Now this is a big enough difference that if this number is like 7.48 something, I'll assume it converges. But if it's substantially bigger than 7.4, like 8.5 or something like that, we will conclude that it diverges, and it actually does. So let's just let that simmer on the back burner as we proceed. We'll come back to, we'll check back in with it, right? All right, so anyway, what we're going to be doing is we're going to be learning how to, without a calculator, without looking at the sequence of partial sums, we're going to learn methods for determining if something converges or diverges. And sometimes that's as good as it's going to get. If something converges, we're not going to be able to find the sum. Very rarely, in just a few cases, we will then also be able to find the sum. So we're looking at the sum of infinitely many terms. Okay, I'm gonna skip that. I'm gonna jump down here. All right. This is called the geometric series test. And as I mentioned yesterday, a geometric series is essentially an exponential function. Okay, but it's in sigma notation. So a geometric series is going to be written of the form, the sum from some index. We use n, typically it could be I, j, or k, but we have some coefficient a times r. We're using r instead of b for the base. We call it the ratio, and it's raised to the nth power instead of the x power. But notice if your sigma has from n equals 0 to something, then n is your variable. So it looks a lot like a times b to the x. It's exponential. The base is what we call the ratio, and the variable is n. Now, we can actually start in sigma notation at any value. That's what's nice about sigma notation. You can define where you start. You can start at n equals 0. You can start at n equals 1. You can start at n equals -1 if you want. You can start at n equals 5, so long as you count by positive ones. We typically don't start with a negative number, though. So here's the deal. Just like an exponential function, if your base, which we call the ratio, is greater than or equal to 1. Well, if you have an exponential function and the base is greater than 1, we call that exponential what? Growth. Those y values are going to get infinitely big really fast. Is there any chance that that's going to converge? No, no way, no how. What if the base is 1? What's 1 raised to any finite power? Uno. So 1 plus 1 plus 1 plus 1 plus 1, is that going to converge? No, it's going to get infinitely large by 1. But, so let's say that. If then your ratio, we're going to call it the ratio, not the base, is 1 or bigger, and that's the absolute value of it, because it could be negative. If the absolute value of the base is 1 or bigger, it's going to diverge. If the base is less than 1, the absolute value of it, that would be like exponential decay. And as we saw with integrals, anything that's exponential decay will go to 0 fast enough, and it will converge. So the series then will converge. Now here is one of the rare times we can figure out not only to what it converges, or that it converges, but to what it converges. The sum, S, will always be, I'm just going to call this the first term. The first term, it's always going to depend on where we're starting. All over 1 minus the ratio. It's always going to converge to the first term over 1 minus the ratio. Not the absolute value of the ratio, but to the actual ratio. Okay? So let's take a look at that on example 8. Using the GST, that stands for Geometric Series Test. You're going to have to determine whether a series converges or diverges, and if it's a free response, you're going to have to cite the test that you use. So if you look at this one right here, what would you recognize this as a geometric series? Yeah, hopefully you would. You might have to rewrite it a little bit. N equals 1 to infinity. You pull the 3 out front, and you're left with 1 over 2 to the n. But that's the same as 3 times the quantity 1/2 to the nth power. So if you can write it in that form, now it fits the geometric series test. 3 would be your starting value, and now you've written it as a base to the nth power. All right, so this is a geometric series because it looks exponential. What is the absolute value of the ratio? It's the absolute value of 1/2, which is 1/2, which is less than 1, right? So the series does what? Converges. Essentially, any exponential decay function will converge. The sum of the terms will go to 0 fast enough so that the sum will converge to a finite number. Now, a lot of the times with the other tests that we're going to learn, we're going to stop right there. It converges. We don't know to what. But in this case, we do. It converges to, how are we going to figure it out? Well, we need the first term. So now we look to see where we're starting. We're starting at n equals 1. So what do you get when you plug in a 1 for n? You get 3/2. So it's always going to converge to the first term, 3/2 in this case, all over 1 minus r. What's our r? 1/2. And then you simplify that, and you get 3/2 divided by 1/2 is the same thing as times 2 over 1, and you end up with 3. So if you were to do the sigma, it would get closer and closer and closer to 3. All right? Let's go back to the calculator and see what it's doing. 9.787, it finished. That is substantially bigger than 7. 1 over n then would diverge. Now let's go ahead and verify real quickly what we just did. Let's go to alpha window number 3. Oops, wrong one. Alpha window number 2. And we'll go from x equals 1 to, we're not going to go to infinity. Let's go to 10. Remember, it's exponential, so it's going to get small pretty quickly. And then we'll go ahead and type in the original format, our rule of sequence, 3 over 2 to the x power. And this will then be the sum of the first 10 terms. When you have a finite number of terms, it'll always be a finite number. Okay, let me go to my mode. The reason it's giving me automatic, it's a nice number. So if you want to have it always give you a decimal, you can go down here, switch to decimal mode. So you don't have to type it in. And now it should give me a decimal, 2.997. So notice only after 10 terms, it's already really, really close to 3. And that's the same thing we saw with the integrals. When it was exponential, it went to 0 so fast that it converged very, very rapidly. So there's numerical evidence to the same conclusion. All right? So that's a geometric series test. If you spot something as geometric, then it will converge if the base, the ratio we call it, is less than 1 in absolute value. Let's look at this one. Is this one geometric? Does it look exponential? Yes. Okay. What is the base? 3/2. So here's what you would write. The absolute value of r is equal to the absolute value of 3/2, which is 3/2, which is greater than 1. So the series does what? Diverges. Yeah, it diverges. This is exponential growth, essentially. It's going to get really big, really fast, and there's no way it's going to converge if you keep adding bigger and bigger numbers. All right, let's look at this guy. Is this geometric, yes or no? It is. If it looks exponential, you have a base raised to the nth power. Now, with an exponential function, if you recall, you weren't allowed to have negative bases. Your base had to be strictly between 0 and 1 or bigger than 1. But that's because we had values of x that were all real numbers, including 1/2. If you raise something to the 1/2 power, it's like taking the square root of it, right? Can you take the square root of a negative number? No. So they weren't allowed in exponentials, but for geometric series they are, because our n is a non-negative integer. So it's a natural number. So -1 to the first, or -1/2 to the first, -1/2 squared, -1/2 cubed. That's fine. You can raise negative numbers to whole number powers. So we can have negative ratios. Do you think this one converges or diverges? Converges. Good. Here's what you'd say. You'd say the absolute value of r is equal to the absolute value of -1/2, which equals 1/2, which is less than 1. Okay, so it's exponential decay. It acts like decay. So, comma, the series converges. Can we say anything else besides that? Yes, it converges to, and now here we go. It's always the first term. The first term depends on where you're starting. We're starting at n equals 2 in this case, not 1, not 0. What do you get when you plug a 2 into the whole thing? You get 3 times -1/2 squared is +1/4. So the numerator is 3/4. And then it's always 1 minus the ratio. 1 minus the ratio. What is the actual value of the ratio? -1/2. The only time we take the absolute value of it is to see if its magnitude is less than 1. In the formula, you have to use the actual value of the ratio. So what's going to happen here is every other term is going to be positive and negative, right? These terms are going to alternate plus, minus, plus, minus. When n is an odd number, it's negative. When n is a positive, it's even. So you're going to be like adding something and then subtracting something, and then adding something and then subtracting something. So it's going to be a little bit smaller sum than if it were strictly positive, where you're adding something. How do you make a sum smaller? You make the denominator bigger. And so that's why it becomes 3/4 over 1 plus 1/2 instead of 1 minus 1/2, okay? So it ends up being 3/4 over, dividing by 3/2 is the same as multiplying by 2/3. So we end up with 1/2. There you go. And you could verify that on your calculator if you want, using the summation. This one converges to 1/2. All right, sweet. Any questions on geometric series? It looks exponential. If the absolute value of the ratio is less than 1, the series converges. If it's greater than 1 or equal to 1, the series diverges. If it converges to the first term over 1 minus the ratio. This is one of really only two, one of only two series that we can actually find sums of, unless we learn power series later on. Okay? So this is what we call a two-way test. The geometric series test is a two-way test, meaning that you can conclusively determine if something converges or diverges. All right? It's definitive. Now, let's look at part B. Without using the geometric series test, would there be another way to determine before we even thought about it as a geometric series, that this one would have in fact diverged. What is the limit as n goes to infinity of the sequence 3/2 to the n? What happens to 3/2 to the n as n gets bigger and bigger? It gets, it's 1.5, right? So because it's growth, the rule of sequence diverges to infinity. If a sequence diverges to infinity, that means when you add up the terms, you're going to be adding up something really big, plus something really bigger, plus something really, really bigger. Does that thing have a chance at converging? No. Okay? So you could determine just because the sequence diverged that the series would diverge. Okay? That's kind of nice. What would have to happen to the sequence at infinity for the series to have even a shot, a remote chance at converging? It has to approach 0. Good. Because if at least the sequence approaches 0, then theoretically there is somewhere down the line where we're going to be adding +0, +0, +0. Now we're never going to be adding 0. We're going to be adding something that approaches 0. But at least in theory, then it would have a chance to converge. Now, just because the sequence goes to 0, does that mean that the sum will be finite? No. We just saw that up here. In both of these cases, the terms will eventually go to 0 because the limit of the sequence was 0 in both of them. So in theory, both of them had at least a shot at converging for their sum. But we just saw that 1 over n didn't go to 0 fast enough. The sum diverged even though the terms did converge to 0, whereas 1 over n squared, the terms went to 0 fast enough for the sum to converge to a finite number. That becomes something known as the Nth Term Test for divergence. Okay? Now, if you were to come up with a mental flow chart of how to approach every single series when asked to decide if it converges or diverges, this would be at the top of the list. This is the first thing that you always look for. Okay? It is a one-way test, unfortunately. It's just a test for divergence. Okay? And here's what it says. It says, if the limit as n goes to infinity of a sub n is not 0, well, what the heck is a sub n? It's the rule of sequence in your series. If the terms then in your series do not go to 0, then the series diverges. Okay? Now, that also means that what if your terms approached 1? What if the sequence had a limit of 1? Would the series diverge? Yes. Is 1 equal to 0? No, because what that means then is if your terms are approaching 1, that means you're going to get to a point way out there where you're going to be going +1, +1, +1, +1 forevermore. And what's going to happen to that sum? It gets infinitely large. So it's a one-way test. It basically says for a series, the sum to have a chance at converging, the terms have to go to 0. But just because the terms go to 0 doesn't mean the series converges. Does that make sense? Okay, so let's try it out. Example 9. Determine whether the following series converge or diverge. If they converge, find their sum. Okay. All right, step 1. Identify the rule of sequence. We're going from 1 to infinity, so it's an infinite sum. If it were a finite sum, like from 1 to 5, it'd be a no-brainer. Then the series converges because it's a finite sum. But it's an infinite sum, which means it still could converge. What's happening to the terms? What's the limit of the sequence? 2n plus 3 over 3n minus 5. 2/3. So eventually, we go out far enough, we're going to be saying plus 2/3, plus 2/3, plus 2/3, plus 2/3. Does that have a chance of converging for the sum then? No. Okay? So you'll say that the series diverges since the limit as n goes to infinity of 2n plus 3 over 3n minus 5 equals 2/3, which is not 0. And if you want to say by the nth term test, you don't have to say that. You're more interested in really performing the test. So again, keep in mind what we're saying. We're saying that the sequence converges to 2/3. But because 2/3 is not 0, the series diverges. Got it? The terms approach 2/3. But because that's not 0, we're never going to have a shot at the series ever converging. All right, sweet. How about this one? Identify the rule of sequence. And if we take the limit as n goes to infinity of n factorial over 2n factorial plus 1, we want to know if this thing converges or diverges. Now, 2n factorial is not the quantity 2n factorial. It's 2 times n factorial. Do you think this plus 1 is really going to have much bearing? No. So this is really growing kind of like 1n factorial over 2n factorial. What would really happen to the n factorials for huge values of n? Well, they'll divide out, right? It's almost like having a 1x squared over a 2x squared. When they're both the exact same, whether they're x squareds or x factorials, this is leading coefficient over leading coefficient. Okay? In other words, if the 1 is out of the picture because it's not really contributing, for large values of n, your n factorials would divide out, and it looks like the sequence is approaching what? 1/2. And it does. So the sequence converges to 1/2, which is not 0, so what? The series diverges. Good. Plus 1/2, plus 1/2, plus 1/2, that's never going to become a finite number. It's always going to be a half larger than it was the previous term. All right, what's about this guy? 3n minus 2 over 3 to the n. You think the minus 2 is really helping for huge values of n? No. So if you kind of ignore it, the limit as n goes to infinity of 3 to the n minus 2 over 3 to the n. Yeah, again, it's like 1 times 3 to the n over 1 times 3 to the n. Leading coefficient over leading coefficient. That is, in fact, approaching 1. So the terms converge to 1. But 1 is not 0, is it? So the series does what? Diverges. It's a huge time saver, okay? Because there might be other ways to determine whether a series diverges, like the geometric series test. But the nth term test is a very quick and fast and easy way to determine if it diverges. Now, if the terms go to 0, then you can't say the series converges. You then say, oh, now the series has a chance at converging. Like on this one, what is the limit as n goes to infinity of 1 over 1 plus 1 to the n? It goes to 0. So does the series converge by the nth term test? No, it's not a two-way test. What we say now is that the series, as you said, might converge, but we have to use a different test. Can we use a different test? Yes. This is actually something that looks very exponential, doesn't it? This is actually a geometric series. 1.1 is the same as 1 1/10, which is 11/10. So that's the same as 10/11. So real quickly here before lunch, is that going to converge or diverge by the geometric series test? Well, 1 over 1.1, if it's the same as 10/11, 10/11 is what in respect to 1? It's less than 1. So it's like exponential decay. So you can go to lunch now. The series converges. And we can actually figure out the sum. And we'll do that after lunch. The series converges. To ... to be continued is what it's to.